Now let's look into inline assembly. So the GNU-C compiler for ARM processors allows to embed assembly language code into C programs. So though we are saying that our course is based on C, we will need to write an assembly language code within C here and there, like in a few places, and that is required because C will not give you direct access to the registers of the microcontroller. So for any reason, if you need to access the microcontroller registers, for example, say you want to do some floating point assembly coding and you want to use the floating point registers, you will not be able to do them directly through C. It is left to the discretion of the compiler whether it uses the floating point register or not, and in such cases you can use inline assembly programming within C to write assembly code which the compiler has to respect. That is, it has to consider that particular code and run that assembly on the controller. So with inline assembly, you can use the same assembler instruction mnemonics for writing pure ARM assembly code. Okay, so this is pure ARM assembly code. The special sequence of line feed and tab characters will keep the assembler listing looking nice. It may seem a bit odd for the first time, but that's the way compiler creates its own assembler code while compiling C statements. So if you're writing within, so this is how it is written. You do an ASM and then you write your assembly code here. So you could do multiple lines of ASM like this, or you could enclose this within brackets. So just do ASM open bracket and write all your commands, and then have a minus \n\t for that is do a line feed, so that, and you can write all your assembly code one after the other. So these are two ways of doing it. Now the general format of an inline assembler statement. Now this is something that this is a little bit complicated, but nevertheless, let's do it. So the general form is ASM, and then you put the code, and then you have the output operand list, input operand list, and clobber list. So this is the code, and we are going to exactly see this code when we see the demo. So what we do is, say we declare one variable here, all word with variables. So variable 1 inline, variable 2 inline, and then variable 3 inline. So variable 3 inline is the output variable. Now we don't want to, in C we could do variable 3 inline equal to variable 1 inline plus variable 2 inline, but say we need to add this value, and we want to do it in assembly, not in C, but we will use these variables. We'll use C variables within our inline assembly. In such cases, what we do is, so first let us go through this. So the assembler instructions defined in a single string literal, okay, and an optional list of output. So these are the meanings of the particular segments here. So code is the assembler instructions defined in a single string literal, looks like this, okay, and then an optional list of output operands separated by commas. So this is an output operand list, and each entry consists of a symbolic name enclosed in square brackets, followed by the constraint string, followed by a C expression enclosed in parentheses. So we'll see all that. And then an optional comma separated list of input operands, which uses the same syntax as the list of output operands. So it uses the same syntax. And then optional list of clobbered registers, which we are not seeing here. This is not shown in the above example. So we have declared these three variables, and so this is the code part. Okay, so the code part is add, and then you do value 1 comma value 2, value 3, which is the output, and then value 1, value 2. So this is the standard syntax for assembly for adding, say, two numbers and putting it into another one. But in this inline assembly, you will see that we are not deciding which registers are being used here. So the registers are actually chosen by the by the compiler. The only thing we do is we ask the compiler to use any two registers as input, and then we give the output operand list. So output operand list is the value 3, which has to be a register, but then we don't know what it is. Okay, so equal to R means it has to be a register. So we are instructing the compiler that you have to put that value in a register, and then we do value 3 inline, which is the output value here. This is a C variable, and then the input operand list is value 1, and this is a register. Variable 1 inline is the variable that we have borrowed from here. Variable 2 is this. So when we run this code, it actually puts these values 10 and 20 and in some registers, that is in some of the 32-bit general purpose registers that we have, but we don't have a control over which register it is putting the value in. And then it puts the output value in some register, and then it copies the value over to var3 inline. So that is what it does. Now we'll see this code in action. Now, in our course, we have rarely used this, and we will not see an instance of this one again. Okay, but this is something that you might need. So I've just kept it here in case you come across such a code in your project, or you are asked to understand or know more about inline assembly. This is one format that you might come across. So for example, what generally happens is you might enclose this in a proper C style function, inside which you have this inline assembly, and you will be passing these values as function parameters. So once you pass these values as function parameters, it does the calculation in assembly and returns the resultant value to you in a C style variable. Okay, so that's the objective of this. Going forward, so to prevent the compiler from removing inline assembly code during optimization, sorry about that, this is you. So during optimization, we use the volatile keyword. For example, if we never use any of the output operands in the remaining part of the C program, the optimizer will most likely remove the inline assembler statement. So we have to, so if we have to force this thing to be considered by the compiler, then we put a volatile keyword. Sometimes the compiler might optimize in order of execution of the inline assembly statements, and that time we make use of clobbered list. So we are not looking into clobbered list now. So volatile is something that we have to do in order to have this definitely executed, so that it does not skip the inline assembly. Okay? Because suppose we don't use the output operands here, it just the compiler is intelligent. It knows that this is, the optimizer knows that there's no point in using this because this is never used, this statement. So it just throws this particular block of code out during compilation. So volatile prevents that from happening. Now there are certain inline assembly constraints. So when passing constants, pointers or variables to inline assembly statements, the inline assembler must know how they should be represented in the assembly code. The constraints are used to control that. For example, F is, when you do F, it means you have to use the floating point registers. This is in regards to this general form of inline assembly. And we have two columns. One is in the arm state and one is in the thumb state. So we'll concentrate on this column. So H means registers R8 to R15. So if you give H option, so if we give an H option equal to H option here, it will use registers R8 to R15. Immediate floating point constant, if you give a G option, not available in thumb. H is same as G but negated, not available in thumb. I is immediate value in data processing instructions. Okay, constant in the range of 0 to 255 as WI operand, and so on and so forth. J is indexing constants, constant in the range of minus 255 to minus 1, like sub R0 operand. Same as I but inverted. same as I but negated. Okay, so these are the constraints that you can put, same as R. M is constant in the range of 0 to 32, and so on. M is any valid memory address. N is not available if this is a constant in the range of 0 to 31. Okay, e.g. LSL R0 R1 operand. So you have to give that value, that constraint there. O is constant, that is a multiple of 4 in the range of minus 508 to plus 508, like this. R is general register R0 to R15. So as you can see here, we are doing R, and since this is thumb2, even though it says it is not available, we can use this in our code because this is thumb2. W is vector floating point registers, and it says not available, but we can use this. Okay, so let us see a demo, and whatever we have claimed and saying that the constraints can be used in the thumb state, let us see if it is valid or not.